We have the sine x. You either already have it, or you could quickly draw it in, and then we're going to talk about what the cosecant of x looks like. So a little reminder, you should have memorized what the sine parent function looks like. So remember, yeah, not lined up good. Yeah, okay. Oh, no. Sorry, I don't know what's going on with my little thingy-majig. To recalibrate. Okay, so we know that the sine function looks something like this. Try to ignore the ugliness of my graph. Make yours better. And we know that now because we have it memorized. But remember, we first saw this because we did a little graphing calculator investigation. We're like, oh, it repeats itself. It just goes through these cycles. Okay, so we figured out it's periodic. That's what we call the functions that repeat themselves like that. The period of the function was 2 pi, and the amplitude was 1. Then we looked a little bit closer about why we're just going to use these 5 points and where they come from. And when we built the parent function on paper instead of using our calculator, if you guys remember, we built a little t-chart where we said, oh, if this is the x value or the angle, when we plug it in and calculate the sine of it, here's the things that we get. And that's how we got the points over there. And so we looked at plugging in like 0, pi over 2, pi, 3 pi over 2, and 2 pi. And so think unit circle. When you plug in 0, what's the sine of 0? So at 0 degrees or 0 radians, the sine there is 0. Okay. Then at pi over 2 on your unit circle, what's the sine? There it's 1. And then at pi, 0. At 3 pi over 2, negative 1. And back at 2 pi, 0. Okay? That's why these points go like this. At 0, it's 0. Pi over 2, it's 1. At 3 pi over 2, or at pi, it's 0. At 3 pi over 2, it's negative 1. And at 2 pi, it's back to 0. Okay? So this was one period of the graph ending at 2 pi. And we talked about how we could divide that by 4 to get our scale, which in this case is pi over 2. And we would count everything off that way. Okay? So that's how we kind of figured out our parent function for our sine. And then since then, we've just kind of memorized it. But the reason I wanted to bring this back is I wanted you guys to understand the cosecant graph. And I think if you understand the sine graph, it makes the cosecant graph a little bit clearer. Okay? So what is the relationship between the sine and the cosecant at any angle? The reciprocal. So if I asked you to find the cosecant of pi over 6, you would go to that place on your unit circle, you'd actually find the sine, and then you'd take the reciprocal, right? That's what you guys would do. We can do that with our graphing also. So instead of learning a new graph to learn the cosecant graph, we are going to get used to what it looks like. But what we're going to do is we're just going to use our old information to create this graph, okay? So I'm basically going to say, what if we didn't want the sine function and we wanted to calculate the cosecant function? What would these points have looked like, okay? So at 0, we wouldn't pick the sine. We would take the reciprocal of the sine. So if at 0 degrees the sine is 0, what is the cosecant at 0 degrees? Undefined, right? Because if you flip 0 over 0, it would be in the denominator, and it would be undefined. How do we mark something as undefined on our graph? Asymptote, okay? Good job, Levi. All right, so we have our asymptote, okay? Then at pi over 2, which is the next mark here, and I'm not going to change the period of the graph because if the cosecant is just the reciprocal of the sine, it's going to start repeating values at the same place the sine started repeating values, maybe just different values because they were flipped over, okay? At pi over 2, we got a sine value of 1. What's the cosecant going to be? What's the reciprocal of 1? 1. Okay, you flip it over, you still get 1. Pi over 2, you get 1. At pi, our sine had a value of 0. What's our cosecant value then going to be? Undefined. We already talked about taking the reciprocal of 0, and it ended up being undefined. And how do we mark undefined on graphs? With our asymptote. Okay. What's the reciprocal of negative 1? Still negative 1. So at 3 pi over 2, we have negative 1. Then at 2 pi, again, the sign was 0, and we already talked about the reciprocal of 0 is undefined, and we're going to mark that on our graph with an asymptote. Okay, so first this kind of looks messed up a little bit, right? It's like asymptote, a random point, asymptote, a random point, asymptote. And these points aren't like the tangent function. It's not like they ended up the same place, right? So then I have to figure out what's going on in between there. Now, once we know what's going on, we never have to look at it again, but I just want you guys to understand it. So that's why I'm going to show it to you. Notice if I pick a point on my sine graph, somewhere between 0 and 2 pi, there is a point right here on the sine graph that has a y-coordinate of like 1/2. Do you guys agree that somewhere in between here there's a point on this graph and its y-coordinate is 1/2? Okay? What's the reciprocal of that 1/2 y-coordinate? 2. So at that same place somewhere between here on the cosecant graph, that point's not at 1/2. It's all the way up at 2. Okay? Then again, after it hits 1, somewhere between pi over 2 and pi, there's another point right here that has a y-coordinate of 1/2. Okay? And that same y-coordinate, if I take the reciprocal of 1/2, it would be 2. So somewhere between here and here, there's another point that's up here at 2. So what shape do you think is happening between these asymptotes? Yeah, it has this, right? But then it doesn't go down like the sine function does. It goes up to these points, and it has to follow the asymptotes. So what you're getting is this parabola shape in between here. Okay? And then this one, yeah, because over here what's happening is somewhere between pi and 3 pi over 2, okay? There's a point right here, and its y-coordinate would be like negative 1/2. If you take the reciprocal of negative 1/2, it's like negative 2. So yeah, on this side, it's going down, okay? Now I know, so this seems really hard, like, ooh, wow, that's a lot. We're not going to do this every time. I wanted to show you this because I wanted you to understand I wasn't just making up the fact that the graph looks like this. It's because of the reciprocal values. But now I'm going to tell you that you actually, as long as you understand that that's where it came from, you don't need to know any of this. You don't have to do this every time, okay? Taking it off, kind of, in a very slow manner. So how are we going to get our graphs like this every time simpler? This is what we're going to do. We're going to graph this. And when you guys don't do it on your graph, okay? But I'm going to put this parent function right on my cosecant graph. I'm going to show you guys the relationship between them, okay? Because visually it's better than it was in the chart. So if I want to get the cosecant graph, I'm not going to graph the cosecant. I'm actually going to graph the sine function. And then all of these points, wherever they end up, okay, shifted, whatever, I'm going to turn all those points that were my zeros along my axis, all those are going to get turned into asymptotes. Okay? And the maximum and the minimum points, they're going to stay the same. And what I'm going to do is just use them as like the vertex of the parabola that's in between the two asymptotes. And that's it. Yes? That your answer is this graph, not this graph. Okay?
But like, you know how you said that like the points on like the line and tricircle are like going to stay?
They're going to stay where they are, but they're going to become asymptotes, not points right here.
But like the points under the half, are they going to move
Like these?
Or like above,
Yes.
like at 2?
So if this moved up 1 or something, so I would move my whole sine graph up 1. But those points that I still know are like on the middle axis, those ones get turned into asymptotes.
And then like you move the little dots?
Yep. So what you're going to do, if someone gives you some crazy, like, long, like, y equals negative 1/2 cosecant 2x minus pi plus 3, okay? You're going to cross out cosecant for a minute, and you're going to live in the world of the sine function. You're going to graph the sine function like you already know how to do, right? Change the period, do any stretches, compressions, reflections. In the end, you're going to get some picture with this shape, but just moved wherever it's going to be moved, right? Then you're going to take all these points and turn them into asymptotes. You're going to keep these points on the graph, but fill parabolas in between the asymptotes that use those points as their vertex points. Levi? As long as you do your stretch with like your sine graph. So if the sine graph was vertically stretched by 2 and this point was up here, that's where the vertex of my parabola is going to be for my cosecant graph. These ones? Oh, these ones here? When we draw it, we're just going to draw this point and fill in the parabola in the right direction. Yes. I just want to know that you guys know that it's in the right area. Okay, so do you get what I'm saying? So this was what I was trying to tell you guys yesterday. We're going to learn 3 new parent functions, but like you're not going to have to memorize these parent functions. All you have to know is how to transform this into its reciprocal so that zeros turn into asymptotes, maximums and minimums will stay there, and what the general shape is so you know where to put the parabolas and stuff like that. Okay? So instead of doing a lot hard work with this new shape, we're going to use the old shape, do all the stuff we already know how to do to it, and at the very end, just transform it into the cosecant function instead. Okay? So period of the cosecant function, just like the sine, its normal period is going to be 2 pi. Yeah, ugly. Okay. 2 pi. And then what's going to happen from there, though, the amplitude is going to be different. Because if this shoots up here and this parabola shoots down here, this function has no amplitude, similar to the tangent that we saw earlier. Okay? So this has no amplitude. All right? So what are going to be the only functions that actually have amplitude? Sine and cosine, yeah, just those waves, because they have these maximum and minimum points, and they're like bound in this one little area. The other ones can shoot off in different directions. Okay? Is this all right with everybody? So now you know the cosecant looks weird. It has asymptotes with little parabolas between. That's what you want to know in your head. Where all that stuff goes, do your sine graph like you normally do, and then where things end up, just transform them. Okay? And we'll do some examples of that later with like some numbers so you can see it, but we just want to get the general idea first. Okay? All right. So then cosine and secant are going to go together also, right? Just like the sine and the cosecant relationship because they're reciprocals. So rather than showing you the chart, the reason I showed you the chart is so that you can understand how the graph was formed. But now that we are like, oh, okay, like that's how the reciprocals go, but there's this easier way, let's try using the easier way this time to figure it out. So our normal cosine function, and again, if you don't have this parent function written down or you're kind of lagging in the parent function area, then use this as like your reteaching tool for what you should have memorized about the parent functions. So just like the sine function, the cosine function had a period of 2 pi and an amplitude of 1. So that meant that this fourth mark was 2 pi, and that if we divide that by 4, we find out our graph is scaled by halves, or pi over 2. So this is pi, 3 pi over 2. So with cosine, the only difference between the sine, it cycled through the same values. It had just kind of a different starting point at 0. Okay? It started at the maximum. And then went through those different point values. Sorry. It like lines up right on that side and not on this side. So we just have to deal for a minute. It's a lot of work to recalibrate it. I have to do it when no one's here. I might fall off a chair or something like that. And you guys would laugh. Okay, so this is our cosine graph. Instead of making a table like I did last time and then like change the reciprocal values, okay, what I'm going to do is I'm going to do what we saw at the end. I know that I can just make the secant graph from the cosine graph. So I'm going to go ahead, I'm going to draw the cosine graph over here, but later on I'm going to end up erasing it because it's not my final graph, but it's going to be my guideline to figure out my secant graph. So I'm going to use the same period that I use over there. So the period is still 2 pi unless it's adjusted by some horizontal stretch or compression. Okay. And again, I'm going to draw the cosine graph, but draw it really light or plan on erasing it later because you know it's not your final answer, but it's going to give you everything you need to get your final answer.
Sorry.
That's okay. Okay. Oh, sorry, Jacob. I forgot. She could have come to you. Are you okay? Okay. All right, so our cosine function cycles through these values. Okay? And it normally looks like this. Now, I'm not going to make it lighter on here because it's kind of impossible for me. I'm going to plan on erasing it at the end, but if I were you, I'd just sketch the cosine curve really light if I was graphing a secant function. Then, if there are any transformations, you'll do all the transformations, and then you'll get here, and you'll go ahead and you'll convert it to the secant function instead. So remember what that means. Any points that are on like the middle axis, even if it's been shifted up or down, So basically these points right here, those are going to become our vertical asymptotes because they're originally at 0 and the reciprocal of 0 is undefined. So those become our vertical asymptotes. And our maximums and our minimums are important to us because the reciprocal is still 1. So these points are in both the cosine and the secant graph. Okay? But we know that instead of getting this wave between, we get these little parabolas that are shooting up and down the asymptotes. So right here, because I know this point is here, I know it'll have a parabola going this way. I know this one will hit this point and have a parabola going this way. Now notice I extended it over here. Technically, if I didn't continue the period at all, you would see this right now. Okay. And then over here, we would get this side of the parabola. Again, that doesn't mean it stops right there. It's not like, oh, that's amazing, it just stops right there. No. Okay, if you continued the cosine wave, you'd get another asymptote right here. So you'd know this go up, there'd be an asymptote, then there'd be one down here, and then an asymptote, etc. Okay? But do you see now, once we've done the chart and we understand how the reciprocal goes, we don't need to do that anymore. We just need to fill in the sine or cosine graph, change all those zeros to asymptotes, then use our maximums and minimum points to know where the little parabolas go between the asymptotes.
The maximum and minimum start with parabolas?
Yes. Those are like the vertex points of them. So they have this point in common. Yeah. So the red is the final graph up here. So yeah, if you know your sine and cosine really well, this won't be too bad. You just have to transform it. Okay? So that's what the secant graph looks like. Again, it looks a lot like the cosecant graph, just like the cosine looks a lot like the sine, just like shifted over or something, right?
Let's say we get like a full problem, like y, in the full problem, like transformations.
Yeah.
Could we do the whole problem in its original
And then just convert it at the end. Yep.
Yeah, we can do that.
Yep. It's beautiful. All right, so Ephraim's question was, if we get some big crazy problem with all these different transformations and all of this, can we still do like the cosine or sine wave the whole time until the very end? And the answer is yes. Okay? You can just graph the sine or cosine, do all the transformations to that, and then at the end change it to the secant or the cosecant graph. Okay? Tangent works the same way, but you guys already know that tangent looks a lot different than sine and cosine, which means like changing it over kind of a lot different. I actually like the way the cotangent graph looks better than I like the way the tangent graph looks. It's actually easier for me to remember the cotangent graph. So I'll be perfectly honest. If someone gives me a very complicated cosecant or secant graph to make, I make the sine or cosine graph and then I transform it. But if somebody gives me a cotangent graph, I don't really start with the tangent. I just start with the parent function of the cotangent because it's actually easier for me to remember it than the tangent function, and I just like to perform the transformations that way. You can totally decide how you want to do it. It works both ways, but just be aware of that, okay? So let's look at what our tangent and cotangent look like. So the difference between tangent and sine and cosine was the period. So the period of the tangent is pi instead of 2 pi. So the fourth mark is pi. That tells us it's scaled by fourths. So remember, the thing that was bothersome about our tangent was we never got to see like the fullness of the way the curve moves, because if we just graphed one period of it, we got like part of the curve on this side, like the point at 0, the point at 1, and then we got the asymptote. And then we got the point at -1, and we got back to this point at 0. So we got these branches like this, okay? It was a little hard to understand then what was happening, so what we often did, not all of us, but some of us, I like to do it. I like to extend it a little bit further so that I understood this was like part of the curve that was then continuing towards the next asymptote. So oftentimes when we graphed the tangent, we kind of started with a period and a half just to give us some idea of what's going on. This is why I like the cotangent better. Its asymptotes are just in such nice places, okay? If this is the tangent function, where are the asymptotes going to be for the cotangent function? What's that? 0. So remember, just like sine and cosine, the 0 points are the ones that turn into asymptotes, right? Same thing here. That means This point's going to be an asymptote, and this point's going to be an asymptote. So same period, because changing it to the reciprocal doesn't change when you're going to start cycling through new values. So the fourth mark on the graph is pi, and that makes it scaled by pi over 4. But again, look at what turns, these had values of 0 in the tangent function, so they're going to become our asymptotes in our reciprocal function, our cotangent. That means there's an asymptote here at 0, and there's an asymptote here at pi. This is why I like the cotangent so much better. Isn't that nicer? Like, oh, the period just happens to contain both asymptotes, and I'm going to see one curve between it, okay? Right here in our tangent function, this is something different than we had because the sine and the cosine had no undefined values. The tangent has an undefined value. How's that going to show up on the cotangent graph? So the things that were 0 here became undefined when we took the reciprocal. So if something started as undefined over here, how's it going to look when we take its reciprocal? So think about it this way. The things that were 0 over here were 0 divided by something. That's how they turned out to be 0. So when we took the reciprocal to put it in the other graph, it meant the 0 would have been in the denominator. That's why it's undefined. Something over here that was originally calculated as undefined already had the 0 in the denominator. So if you take that and you flip that over, 0 divided by any number is going to be 0. So anything over here that was undefined will become 0, just like the zeros became undefined. Like they're kind of swapping places. Okay, so where this asymptote was over here is now going to be our 0 over here. So that's so nice, right in the middle of the period of the cotangent function. And then look, we still need points at pi over 4 and 3 pi over 4, so I'm going to see what happened over here. At pi over 4, we got a y value of 1. The reciprocal of 1, as we talked about earlier, is just 1. So this is here. And at 3 pi over 4, the point was at a y value of -1, and the reciprocal of -1, like we talked about before, is just -1. So that means this looks like this. So here's what I was talking about before. For sine and cosine, I feel like it's a lot easier to use the function you're used to, transform it, and change it. But for tangent and cotangent, I feel like it's kind of a toss-up. I personally just learned this. I think it's actually much easier than learning this one over here because it starts and ends with the asymptote, and the curve just goes the opposite direction, appears to go the opposite direction of the tangent function. So when someone gives me a cotangent to graph, I just start with this, and then I transform it. I'm not saying you have to do it that way, but you decide, like, no, I know the tangent so well, I'm going to start with this, and then I'm going to make all the changes, okay? Or, like, this one's not that much harder to add to what I know, so I'm going to go ahead and add this in. And I barely ever say that I know something. You know, normally I'm all about, like, transforming it because I don't have a lot of space up here in my head like all you young people do, okay? But this one, I don't know. There's something about it that it's easier for me than dealing with that one, okay? So individual opinion, you guys can decide to do what you want to do with it, all right? So what we're going to do is we'll go through graphing one of each one, so like the secant, the cosecant, and the cotangent. So you guys can see with like the stretches and compressions what would happen, okay? Are we good with all the parent functions? Again, none of the reciprocal functions have amplitude because all of them have something that shoots up and down. The tangent also does not have amplitude. So the only thing that has amplitude is the sine and the cosine functions, okay? And after today, you guys are technically done with the whole unit. Like, this is the last new thing we have to learn. But we're not testing. What's that? No, the unit. So, yeah, we just cut it off early in here, like March. When March is done, we're done. No. All right. So let me ask your guys' opinion. I gave you mine. I wasn't meant to sway you. I told you could decide how you want to do it. But how many of you guys now, when you see a cotangent function graph, how many of you are going to start with the tangent function, do that, and then change it to cotangent? Okay. How many of you guys are just going to start with the cotangent and do it that way? Okay. All right. So I'll do it both ways since we have people doing both things to make sure you understand kind of the different little ins and outs of doing it that way. if you start with the cotangent function, it's going to be the same as it's always been. You're going to have a memorized parent function, okay? You're going to adjust the scale with any horizontal stretches and compressions and then do any other changes that are there. So if I was going to do this by knowing the cotangent parent function, I would start by saying, okay, normally, what's the period of the cotangent? Pi. Okay, same as period of tangent. I'm going to multiply it by the reciprocal of any horizontal stretches and compressions. So in this case, I see 1/2 right here. I'm going to multiply this by 2/1, okay, making it a horizontal stretch because now my period's going to be 2 pi. Okay, just like all the graphs are. Yeah, sorry, Micah, go ahead.
So does the theta act as x?
Yes, it's just like x. Sorry, yeah, thank you. Theta is just like x. They often use it when we're plugging in angles. Like if you guys are in physics and stuff, usually they use like the theta as like the angle measurement for whatever their vectors and different things that they're using. So this means if the period is 2 pi, the fourth mark on my graph is 2 pi. And again, I scale that how I always do. Fourth mark is 2 pi. If I divide that by 4, I can know what I'm counting by along my graph. 2 pi divided by 4 ends up being pi over 2. Okay? So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and I could keep going, right? 5 pi over 2, whatever I want. If I have the cotangent parent function memorized, I know it starts and ends with an asymptote before any shifting or anything is done. That this middle point here is 0, and it curves the curves seem to look the opposite direction as tangent. So they go up, middle, down. Okay. So there's my parent function. Okay. This is if I memorize the cotangent parent function. And for those of you that are like, no, I like the tangent function, we'll talk about how you could do that in a minute. Okay. The only other change here is this 1/2 that's in front of the cotangent. What is that 1/2 going to affect? Vertical. Okay. And it's going to do what vertically? Compress. Okay. So these points that were 1 unit away from this kind of axis here are now only going to be 1/2 unit away. So here and here. This point stays because it was on the axis. So it's just going to kind of make our curve appear wider. Okay. All right. And at this point, I do want you guys to get used to adding another period to your graph. Okay. All that means is continue counting. So this was 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. Okay. I can't count very well. All right. And then you just need to repeat. So with tangents and cotangents, you're just going to go, there's asymptote, there's 3 marks between, and then the fourth mark's an asymptote. So asymptote, 3 marks in between, fourth mark is an asymptote, okay? And then follow the pattern of points that already existed. Higher, middle, lower, okay? Higher, middle, lower. But using the distance that our problem said, these were only at 1/2, they're not at 1, so that's what I used. And there would be a second period of my tangent function. Eventually, I want to see you graph 2 periods of sines, cosines, tangents, all those things. Okay, so you understand they don't stop somewhere or whatever, and you understand how to cycle through the points. Okay. Is this okay with everybody? That's going to memorize the cotangent? Mallory?
I don't get why, for the vertical compression, why isn't it 2?
Good. Okay, so really good, because you're using the tangent function first, right? You're thinking about the tangent function, and then, so is it?
I want to do it like how you just said it, but like I don't get why, like once you have a vertical compression, like why isn't it 2? You know how we
Yeah, so for all the horizontal stuff, it's kind of the opposite of what you think, but the vertical stuff is very straightforward. And the reason is the horizontal stuff multiplies like the x value before you ever take the cotangent. So like normally, let's say, we would reach 0, like we'd get 0 when we took the cotangent of pi over 2. Okay, so normally the cotangent of pi over 2 is what gives us 0. But now when we put in pi over 2, it would get multiplied by 1/2. It would change it to pi over 4. Okay? So now when we put in pi times 1/2, we're actually getting pi over 2 and taking the cotangent of it. So it's actually making it happen at a different place. We did this at the beginning of our other transformations when we plugged them in.
And so like the very outside of that 1/2.
Yeah, so what...
How it
Yeah, because what that does is after you've already calculated all this, and normally right here you get a 1, right? It's now saying you have 1 times 1/2. And 1 times 1/2 is just making it go to 1/2. This one's more deceptive because it's like moving the number before you do whatever it is you're going to do to it, like take the cotangent or the tangent. No, you make it to 2. Yeah, so all the vertical stuff is pretty straightforward. Whatever's there, that's how you're going to use it. And all the horizontal stuff is a little tricky. For the multiple stuff, for the multiplication, we use the reciprocal. And when it says like plus pi, we actually go to the left pi. But if it said plus 5 at the end and it was vertical, we'd actually go up 5. Okay? Yeah, Scott? It's a vertical compression. Okay? And so this is something I want to mention, though, for those of you that want to start with the tangent function. So those people that are like, no, I'm going to start with the tangent function, then I'm going to graph it. I do want to mention one thing so you don't get confused about the 1/2 that's in front, because that is going to change. If you used the tangent function and then changed it into the cotangent, you would still adjust the period the same. So this would be 2 pi. You'd divide that by 4. And you would signify that normally our tangent function looks like this. Right? And then you would want to go and transform it to the cotangent. Now be careful with this 1/2 right here. You already took care of this one by just changing the numbers along the scale. This one is where it gets a little tricky. You can't change these to 1/2 and then take the reciprocal of 1/2 and say that that's getting stretched all the way up to 2. And the reason you have to think about the reciprocal before you compress it, think about what you would be doing here. You would be calculating the cotangent, which is the reciprocal. Then you would multiply by 1/2. So the reciprocal of 1 would still be 1. Then it would get multiplied by 1/2, making it 1/2. You wouldn't say 1 times 1/2 is 1/2, and then I'm flipping it over to make it 2. Like, no. So it should still be compressed, just like you would see before.
So the 1/2 in front is the horizontal, and the 1/2 after the cotangent is...
No, this is the horizontal, and this is the stretch, and that's what came right here.
But that's for the scale.
Yes. This is a vertical compression, and so what that's going to do is once I change this, for those of you that started with the tangent, when you change this to cotangent by going like this, and saying, oh, this reciprocal is itself, and this reciprocal is itself, and you can see the cotangent right here. Okay. Then you still have to do that 1/2 compression. Okay? The sine and cosine is not as confusing. You can do everything to the sine and cosine wave and then change it, because when you do it that way, you're not messing up any of the order. But tangent and cotangent can be a little tricky. So just make sure that these points ended up at the 1/2. Okay? Are we good with cotangent graphs? All right, so then we want to graph this. Before we graph this, this is what I all want you guys to try and graph on your paper. So this should be review for the moment. It's almost like I'm changing the problem, but at the end we're going to go back to this. Now, keep in mind as you graph this, that whatever you get for this final graph, either make it really light or prepare to erase it at the end, because our last step is going to be to actually graph a cosecant, okay? But to graph the cosecant, what we really want to see is what does the graph of negative 1/2 sine of 2 theta look like, okay? So use this as a moment of review or like a self-test about how you would do on the quiz on Friday. So there could be a problem just like this on there. Can you find the period of this, scale the graph correctly, and get a period of this onto the graph correctly marked, and then we'll work on transforming it to the cosecant, okay? So do that first. Go ahead and... All right, so checkpoint. Did you do the sine graph right? So what you should have got as your new period for this function would come from taking the normal period of 2 pi, and because of this 2, multiplying it by 1/2, which would create a period of pi. So your scale should be by fourths, okay? Pi over 4. Okay. Your normal sine function would follow this pattern of points. 0, up, 0, down, 0, okay? But two things are happening because of this stuff in front of the sine function right here. The negative is causing a reflection, so things that are maximums are going to become minimums. Okay? Shh, you guys in the back for the other people that need to hear. Okay? So the things that are maximums are going to become minimums. Things that are minimums are going to become maximums. And this is going to compress it so that instead of them being 1 unit away from that kind of central axis that we have, they're only going to be half a unit away. So this point that was a maximum will now become a minimum, and it will now only be half a unit away. Okay? And this point that was a minimum will now become a maximum, but again, it will only be half a unit away. So this, and I'm going to draw it dashed because you guys can draw it real light on your paper or whatever. That's what the sine graph should look like. Okay? How many people feel like they were successful with graphing the sine function? Good. Then the quiz should be good. All right. Now how to transform it to actually a cosecant function. So now our goal is to actually graph the cosecant, so we want to get the pattern of points that that's going to follow. And we should have in our head from the graphs we saw at least an expectation. We expect asymptotes, right? And we expect little parabolas between them. Okay? Yes?
So all the asymptotes are always like the line, pretty much like on the line of symmetry.
Yes. Okay? Yeah, so wherever this axis, even if it gets shifted up or shifted down, those points that stayed along that axis are going to transform into your asymptotes. So yes, I have an asymptote here. I have an asymptote here at pi over 2. And I have an asymptote here at pi. Okay? And then the points that where your maximums are minimums are also included in your reciprocal function. So this is a point on my new graph, and so is this. Okay? But this tells me that this is going to go like this. And I don't need any other points in here. I'm good with that. Okay? And that this is going to go like this. Okay? And then you can erase that middle one. If you leave it really light and dashed, and I understand that you know that's not actually part of the graph, I'm okay with that too. Okay? Is this all right with everybody? All right? So you really have to rely on your sine, cosine graphing to be able to graph secant and cosecant. And then you're going to make a decision about the tangent. You're either going to really rely on the tangent to get the cotangent, or you're just going to memorize the cotangent function because it's not that difficult. That's totally my personal opinion. If you don't feel the same, it's fine. This way? But the cotangent, memorize it.
I can memorize the cotangent.
I know. That's how I feel about it, too. All right. Last one to try before you guys leave. We'll just let you work on this one individually. Y equals the secant of 3 theta. So it says secant. What are you going to graph first? Cosine. So pretend for a minute like it says y equals the cosine of 3 theta. Make that graph and then transform it.